Hi, my name's Francis MacDonald, and I am with Kenorland Minerals. I'm the Executive Vice President of Exploration and one of the co-founders of the company. And it's a great honor and pleasure for me to be talking with the UBC Dawson Club because I went to UBC myself, I guess 12 or 13 years ago. And so it's great to try and engage with people who are at a few steps behind where I was a little while ago. So I'm going to be talking about Kenorland Minerals, the exploration that we're doing, which is mostly early stage greenfields exploration, and some of the strategies that we employ, and then also talking a little bit about some historic compilation work that we've done that I think helps understand the aims of an initial drill program into greenfields areas, and contextualize some of the things that you might see in press releases or in company presentations about drill intersects and what they mean for the potential for a deposit to be defined down the road. So I guess a little disclaimer, this is don't take what I say as investment advice. And then an additional disclaimer, so a lot of the data that has been compiled is coming out of a whole bunch of different sources. So assessment reports filed with the government, academic papers, press releases, articles in the Northern Miner. And for the drilling study, best efforts were made to use primary data. So this would be drill logs and assay certificates. And because this data is historic, we're not responsible for any inconsistencies or errors in the data set. So I'll start out with looking at Canada and where the greater than 2 million ounce gold deposits are. So in Canada, there are 83 deposits that have gold as a primary commodity that are greater than 2 million ounces of gold. And so this is excluding all of the copper dominant porphyry systems, which would be in British Columbia a lot of the time. So using a 2 million ounce cutoff, the current resource and reserves and historic production in Canada total 654 million ounces of endowment. And most of these ounces are hosted within 6 geologic domains. And so that's 87% of that 654 million ounces, which are hosted in the Slave Province of about 50 million ounces, the Golden Triangle, 118 million ounces, the Uchu Birch domain, where there's 63 million ounces, which a big percentage is out at the Red Lake deposit. The Wawa Wabagoon terrain has about 57 million ounces. The southern Abitibi, 223 million ounces. And then the northern Abitibi has about 55 million ounces. So most of these areas are Archean greenstone belts. And so Archean greenstone belts in Canada host 75% of the total gold endowment. And then the Golden Triangle hosts about 18% of total gold endowment. So if you are thinking about where to explore in Canada for gold, it's probably best to be in Archean greenstone belts or in the Golden Triangle. So when we break all of these 2 million ounce deposits down, I've classified these as either greenfields discoveries, brownfields discoveries, or historic discoveries. And so I'll start with historic. So these would be deposits that were discovered by prospecting, typically before 1950. And examples of that would be the Dome deposit in the Timmins camp. And the Timmins camp has produced about 70 million ounces of gold. And a lot of that was discovered in the early days of prospecting in the early 1900s. Then we'll go to brownfields. So brownfields are deposits that are discovered nearby existing significant gold deposits. And an example of this would be the Canadian Malartic deposit, which was discovered in 2005. This was discovered around the Malartic complex, which had historically produced about 5.5 million ounces of gold. And then Osisko went in 2005 and discovered Canadian Malartic, which is a large low-grade system, which is about 20 million ounces of gold. And then greenfields, so these are deposits that are discovered in areas with no significant known gold deposits. And so these are completely new areas that have been opened up by greenfields exploration. An example of that would be the Eleanor deposit, which was discovered in 2004 in Quebec in the James Bay region. And this was discovered by tracing glacially transported boulders back to the source. And so when you group all of the 2 million ounce deposits in Canada into these three categories, it's roughly about the same number of ounces and the same number of deposits. So equal proportions for greenfields, brownfields, and historic. When we look at these discoveries by decade and plot up when these groupings were discovered, obviously before the 1950s, this was mostly historic and some brownfields discoveries. So this would be the Kirkland Lake Camp, the Timmins Camp in Ontario, the Val d'Or Camp in Quebec. So these are the long producing districts in Eastern Canada. And then in 1950s, after World War II, this is really when, what we think of modern exploration getting started. So people are sampling boulders, people are sampling soils, and airborne geophysics is starting to be employed after the Second World War as well. And so as we go on in decades, you can see the proportion between greenfields and brownfields. In the 1980s, there was quite a few significant greenfields discoveries, and this was probably fueled by the introduction of flow-through financing as a tax incentive in Canada. And so that funneled a lot of dollars that were looking to get the tax benefit into exploration. So the 80s and 90s, there was quite a few greenfields discoveries. And then in the 2000s, it really started to fall off. And then when you get into the 2010s, discoveries in general have been on a downwards trend since the 1980s, and there are really only 5 greater than 2 million ounce deposits that were discovered in the 2010s. From 2000 to 2020, there's only a total of 5 greenfields discoveries as well. And so why is this? And I think our take on it is that grassroots or greenfields exploration has been underfunded relative to brownfields exploration. So this graph is pretty important, and it's introducing this concept of GT, which is grade times thickness. And so when you have a drill hole, you would take the mineralized interval, so the length of the drill hole, and multiply it by the grade. And so if you have 10 meters at 10 grams per ton, that would be 100 GT. And so what this graph is showing is all of the GT intersects around or into these greater than 2 million ounce deposits in Canada. And this data was compiled out of assessment reports, press releases, basically any data source that might have this kind of information. And so when we look at this, you can see there's a huge variation to what the initial or the best initial drill intersect is into a deposit. But when we have this data, we can start to look at it statistically. And so one very easy thing to do is plot up the median. And so the median is 134 GT for a discovery hole, and the 80th percentile is 75 GT. And so what this is telling you is that if you have a greenfields exploration project or a brownfields exploration project, if you're hitting drill intersects that are 134 GT, 150 GT, then that is probably very significant for an initial drill program into a new target. So there's quite a few other metrics we can look at. So on this graph, this is GT versus total gold endowment. And it's also, there's quite a big range across this. But when we look at this, there's a few conclusions we can take from it. So the majority of greater than 5 million ounce deposits have GT intersects greater than 134 GT, which is the median intersect. And so this and these GT intersects can be used to evaluate early drilling into gold prospects. Another significant outcome from this is the intersect length versus gold endowment. And so I think this is really one of the more important things that came out of this. So in most modern world-class gold deposits, the grade doesn't vary significantly. It could be from, let's say, 1 gram to 10 grams per ton, so one order of magnitude, but the tonnage can vary vastly. And so it's really the tonnage that's driving the gold endowment a lot of the time. And so when we have an initial drill program into a new area, there's really only one dimension that we can define, and that's the length of the drill intersect, or the length of the mineralized zone in the drill core. And so from this, we can make some conclusions. So most of the greater than 5 million ounce deposits on the initial program, they have a thickness of more than 10 meters. And most of the 2 million ounce deposits have a thickness of more than 5 meters. So that's just kind of some ballpark rules of thumb. You know, really look for those areas that have 10 meters wide of mineralization. And so this is obviously dependent on the deposit type. So big porphyry systems will have a lot longer intersects that could be hundreds of meters long. And so this is really kind of geared more towards structurally controlled deposits, where we're looking for vein deposits that have decent grade that's mineable underground. So this is back to the GT intersects of all of these deposits. And Kenorland has been exploring our Frotet project with our joint venture partner Sumitomo since 2018. And on the initial drill program into a completely greenfields target, we intersected 29 meters at 8.47 grams per ton, which would be 247 GT. And that was including 11 meters at about 18 grams per ton. And so when you plot this up in the GT space with all of the other significant deposits, this is sitting somewhere around Canadian Malarctic, Barkerville, Caribou, Coffee, or Snowfields. And so this is obviously a really significant drill intersect on an initial program. In this area, there were no historic drill holes and no mineral occurrences, so this is really a bona fide greenfields discovery. And this is what we're following up on right now, currently drilling 9,000 meters of follow-up into this target. So I'll talk a little bit about the Frotet project. This is a simplified geology map of the Abitibi Greenstone Belt, where the green rocks are volcanic rocks and the gray are clastic sedimentary rocks. And so the Frotet project sits to the north of the Abitibi Greenstone Belt in a smaller belt called the Frotet-Evans Belt. It covers about 40,000 hectares currently of that greenstone belt. Kenorland, we acquired this in March of 2017 through map staking. And just a little more about Kenorland. So we're the largest mineral claim holder in the Abitibi, which is the second biggest gold producing district in the world. And we identify geologically prospective areas with low exploration maturity and acquire them through map staking. So that has been the strategy up until now. So this is a magnetic map of the Abitibi, and so I think the important thing here is that there are these curvilinear east-west trending deformation zones that transect the Abitibi. In the southern part of the Abitibi, these have been recognized for a long time as controlling a lot of the gold endowment. So around Hollinger, which is the Timmins camp, that is the Porcupine-Dester deformation zone, and on that structure there's probably about 90 million ounces of gold. And then to the south, this is the Larder Lake Cadillac deformation zone. The Kirkland Lake camp is here, which is about, I think, 40 million ounces, and the Val d'Or Canadian Malarctic camp is about 40 million ounces here as well. So lots of gold endowment on those structures. And then as you go northwards into the Abitibi, there are other east-west trending deformation zones that may or may not have gold on them, and those deformation zones are probably prospective. And then as you go further north into the Frote-Evans belt, you can see that there's a big east-west structure that transects the whole Frote-Evans belt. And so this is these are some of the criteria that we use for selecting ground. So proximity to big east-west structures is a big one in the Abitibi and Frote-Evans belt. Another thing that we do is try to quantify exploration maturity. And I think really this is one of the most important things, is that in order to be successful, I think you have to look in places that people haven't looked before. And especially when you're doing greenfields exploration, you really want to focus on areas that haven't seen a lot of exploration before. And so what this map is a drilling density map of the Abitibi. And so here you can see there's some really bright areas down in the south. Obviously, there's a lot of gold deposits down here, and so they've seen a lot of drilling. And as you go to the north, you see some other little areas that are bright. So these may have small gold deposits around them, or they may not. And that would tell you that, you know, they've probably been adequately tested because there's quite a bit of drilling around and not much has been found. So zooming into the property scale, this is the simplified geology of the Frote-Evans belt. And so it's a typical greenstone belt succession where we have multiple cycles of tholeiitic and calc-alkaline volcanism and magmatism. Right now, we think that the favorable unit is this light green unit, which is a big calc-alkaline intermediate to felsic volcanic package. And within that, we're seeing at Renault that we're getting these subalkalic intrusions that are popping into it as well. So within the belt so far, we have identified 4 target areas, and Renault is the most advanced so far, where we had the most excitement. And so this is high-grade gold hosted in a multi-phase intrusive complex. The Cressida area is up here in the northwest of the property, and that's on trend from the Troilus deposit. And that has an extensive gold and soil anomaly that's on trend from Troilus and also their new southwest zone. And so that has yet to be drill tested. The Chatillon target is on the northern side of this intermediate to felsic volcanic package. And there's a 1 kilometer by 1 kilometer mineralized and altered boulder field with grab samples up to 22 grams per ton gold. And then the Lafourche area is up here. And so that's a huge soil anomaly in bismuth, tungsten, tellurium, moly, cesium, thallium, and potassium. And that's 1.6 kilometers by 1 kilometer, and that's yet to be drill tested as well. In terms of the mag, so this is magnetics map, and this gives an idea of the structural trends and potential architecture that you see in the belt. And so on this map, I think you can see 2 dominant trends. So in the south, everything's trending east-west down here. And that's important because everything in the northern Abitibi is also trending east-west. And this is when the Opatica terrain and the Abitibi terrain collided at about 2700 MA. And there's documented north-south compression, which forms this east-west fabric that you see. So that was the gold event in the northern Abitibi around the Detour Lake deposit, which is 20 million ounces of gold. And so we see the same kind of structural fabric that we see around Detour. And then also in the northern part, you can see this northeast trend. And we think that is important as well. We think this is probably an early deformational event. And Troilus, which is a 7 million ounce gold deposit, is sitting on one of those big east-west, northeast trending structures up here. I think the interesting thing about the Renault area is that the structure completely jogs or bifurcates in this area. So out here, everything goes east-west, and then it all kind of wraps around here and jumps up to the north and continues east-west. And so the Renault target is sitting right in that structural jog where the east-west structure does a big jump. This is the superficial geology of the Froted area, and so green is till, and orange is glaciofluvial or esker and outwash deposits. And so the important thing here is that most of the belt is covered in glacial till, and that's important because sometimes till can be very useful for mineral exploration. And this is a kind of schematic of what mineralization is doing in a till covered terrain. And so down here you can see this is the bedrock, this is ore zone, and as the ice pushes all of the material during the last ice age, you can see that it kind of makes this ribbon or tail from the ore zone up to surface. And so what we've been doing is till sampling and looking for this dispersion plume in the till. The general ice direction is towards the southwest up here. You can see all of these streamlined landforms in the DEM. And so this was probably one of the more important exploration steps, was deciding to till sample, because we have a big geochemistry signature in that. And so this has been used before to find a number of deposits, the Lac de Gras diamond deposits in Northwest Territories, the Rainy River deposit in Ontario, Casa Berardi. Eleanor was found by tracing boulders that were in till, and then some other ones are the Strange Lake rare earth deposit and the Renard diamond deposit in Quebec. So this is the sampling grid that we did on the first pass, and it's showing gold in soils, and so these are the cutoffs on the left side here. So the line spacing is about 1.5 kilometers on the initial survey, and the sample spacing is 150 meters. And so we did that in the summer of 2018 across an original land package that was 56,000 hectares. And we covered the entire property with 2,300 samples. After that, we dropped ground that had no gold on it. And so that's why the claim boundary looks like this now. And then in 2019, we infilled on 4 areas. And out of those 4 areas, I think 2 look really good. And so that would be the Renault area in the south and the Cressida area in the north. And so obviously Renault is the highest ranked target. And so in this area, there was no historic mineral occurrences ever recorded, and no historic drilling either. So we went in there and started prospecting and looking for boulders. And this is what we started finding. So we sampled about 140 boulders in the Renault area. In terms of statistics, so there was 10 samples over 10 grams per ton, up to a max of 408 grams per ton, 23 samples over a gram. And so what this was doing is, we knew there was gold in rocks. We knew there was a high concentration of boulders that had gold. And so we started looking at what that mineralization looked like. And so what we see is that most of the time it's associated with quartz veins, the veins that could be sheeted veins, that could be stockwork. And then we have these kind of more brecciated veins as well. There's 1 to 5% disseminated sulfides, and there's also biotite alteration, and the host lithology is a diorite. So I think this was really essential, was looking at the boulders, because we got a good idea of what the mineralization looked like and how to target with the geophysics. This is looking at the geochemical layers that we have. So on the left side, this is soils, or this is B horizon soils with a till substrate. This is gold grains, so we are counting the number of gold grains that you can get in a 10 kilogram sample. And then this is all the boulders that we collected. So you can see there's a couple areas that have quite a bit of golden boulders here. And so they're really all kind of in the same areas. So this is kind of telling us, when you have overlapping data sets in areas, that's really good. The soil geochemistry was really used to define the spatial extents of the glacial dispersion trains. So you can see to the north, we have no gold in soils, and so we did really high density soil sampling to define this area. The boulders were used to understand the grade of the gold in bedrock, and then also to understand the physical characteristics of mineralization. So that would be stockwork quartz veining, disseminated sulfides, which you can target using different geophysical surveys, which I'll talk about. The southern portion of the Renault area, which is this whole block down here, is about 2.5 kilometers. There's been no drilling done down here to date, and so we're just starting to drill test some targets down there. And then one other thing is that the morphology of the gold grains can be used to get an idea of how far the source is. And so the concept is that gold is usually very malleable. And so when it's at the base of the glacier and getting ground up by the glacier, the gold grains will change morphology. And so if you see gold grains that have really rounded edges, that probably means they've traveled quite far. But if the gold grains are pristine looking, then it probably means that they're close to source. And so we're trying to use gold grains to give us an idea if there's multiple sources in here. And so we think down in the south, we see the gold grains counts and the morphology decrease around here, and then it picks up again down here. So we think that we have probably another source of gold in bedrock down there. So this is looking at the geochemistry, geophysics, and interpreted geology. So where we have the soils, this is all coming off of this trend. And in this trend in the magnetics, it looks like it's a big intrusive complex. And this is what we've hit in drilling so far. So this is our current interpretation of the intrusive complex, which is about 4.5 kilometers long. We've only hit significant gold in intrusive rocks or diorites mostly so far, and they're actually monzodiorites. And the mag suggests that it continues to the southwest, as do the soils. So we're doing some work down there right now. So initial drill results, we've drilled kind of just, random holes targeting geophysics anomalies over a 2-kilometer strike length. And so the best intersect was right here. That was 29 meters at 8.5 grams gold. On the west side of the lake, we hit 2.7 meters at 33 grams gold. Up here, we hit 2.6 meters at 10 grams gold. Down here, 3.75 meters at 16 grams. So we're really hitting gold all over the place. And this is a huge area with very little drilling so far. So right now, we've drilled a total of about 7,800 meters so far. And right now, we're drilling another 9,000 meters. So chargeability, this has been really important because from the boulders, we knew that there was disseminated sulfides in the diorite where we see gold. And so with IP and chargeability, that's what we're targeting is disseminated sulfides. So this is a chargeability map 75 meters below surface, and this has really driven a lot of our drill targeting is because we're looking for those sulfides, so we're always kind of staying close to these chargeability anomalies. And we've since tightened up our IP grid, so we have this map here was 200 meter spaced IP lines, and right now we're doing a 50-meter IP survey across the whole area and down to the south as well. And then one other thing is that chargeability within the volcanic rocks hasn't returned any significant gold to date. So it's really, we're looking for chargeability in the intrusive rocks. So this is what that, the best intersect looked like. And so you can see this is similar to what the boulders look like. So it's you can't see the biotite here, but it's black and biotite altered diorite that has quartz veins in it. And about 3% disseminated pyrite over this whole 29-meter interval. And then one thing in here is that the wall rock is carrying significant gold. So you can see this sample right here hit 9.1 grams per ton with very little veining. So that's quite important because that could mean that there's good tonnage that could be developed here if the wall rock has gold. So in terms of geologic summary, the host rocks, so there has been significant gold intersected in diorites to date. The lithogeochemistry that we've done has defined a number of different phases. in the intrusive complex. So there's at least 4 different phases or chemical phases. And then veining and mineralization typically form at internal contacts between different phases in the diorite. So that gives us another targeting criteria. In terms of structure and mineralization style, so high-grade gold hosted in quartz calcite veins. The veining occurs as stockworks, sheeted veinlets, and massive quartz veins. The gold hosted in wall rock, there's gold hosted in wall rock with very little veining and associated with disseminated pyrite. And also we have these zones of pyrite only or massive pyrite that are running high-grade gold. And then in general, the intrusive complex is quite low strain, but in mineralized zones, there's a moderate to intense foliation developed. In terms of trace element geochemistry, so the gold has a 1-to-1 correlation with silver and tellurium. And so that may indicate that we have tellurides in the system. And then there's a weaker correlation with bismuth, moly, tungsten, sulfur, and copper. And where we see chalcopyrite, that's usually where we're getting high-grade gold. And then another interesting thing is that the gold-silver ratio is highly variable, and most of the time silver is higher than gold, which is somewhat atypical of orogenic gold deposits. The alteration is biotite calcite, and that's pretty ubiquitous around the mineralized zones. In terms of geophysical properties, so chargeability anomalies within the intrusive rocks have produced the best drill results, or the drill intersects. Chargeability anomalies in volcanic rocks haven't produced any significant intersects to date. And then also we have these remnantly magnetized intrusions that seem to have gold along their contacts. So that may be important. In terms of paragenetic characteristics, the mineralization and alteration seem to be fairly early in the sequence. And so we're kind of still working out the whole sequence of events of going from volcanism and magmatism all the way up to the end of the orogeny. So just going back to the drilling case study, to put this in context, this is the Quebec provincial drill database. So this has 156,000 drill holes that have been reported from exploration assessment reports. And so most of the time, assessment reports are only filed in the early days of exploration, because once there's enough work done on the credits, they don't have to file work anymore. So these are really records of the early stage exploration that's gone on in Quebec. And so the idea here is to look at the entire Quebec drill hole database to see what's significant and what's not in terms of early stage drill results. So these are GT intersects of the whole Quebec database, the 156,000 holes. And so the drilling at Renault is up here. And so these lines are a couple metrics from previous slides. So the intersect length greater than 10 meters here, and then the median GT. So this upper right hand quadrant is really the significant intersects. And so you can see where Renault plots in comparison to the Quebec database. And then also these are colored by different deposits. And so you can see some of the well-known deposits: Canadian Malartic, Casa Berardi. Fenelon is a new rediscovery by Wallbridge. And so the Renault drill intersect on the first pass sits up in here. So that looks like similar to these other major deposits in Quebec. So we think that this is pretty significant. And so what we're doing right now, we're just completing a big IP survey in this yellow block, and then we're drilling 9,000 meters within these areas A, B, and C. So I'm going to jump over to Alaska right now, because we have 2 projects we're going to drill in Alaska this year. This is the Tanacross project, and this is a copper, gold, moly, porphyry target. And so Tanacross is sitting right on the Yukon border in Alaska. It's in the Yukon-Tanana terrain. And it sits at this intersection between these origin parallel structures, which are going northwest, and origin perpendicular structures, which go northeast. And so those intersections are usually a good place to put porphyries. And a good example of this is the Casino deposit, which is a 2 billion ton porphyry deposit, and it sits right at that intersection as well. So looking at the magnetics, in this you can see some of the structural framework. This is the Big Creek Fault, which goes up to the northwest, and then the 60-mile Pica, which comes up to the northeast here, and we have this big mag high that's kind of sitting underneath the Tanacross project here. And so what this is the upward continuation of the magnetics. So it's looking at about 10 kilometers down, and what we see is that there's a big, deep magnetic high underneath Tanacross. And so the idea with that is that it's probably a big oxidized or magnetic batholith. And an example of where that's important is Pebble. So we upward continue the mag at the Pebble deposit as well. And so you can see that underneath Pebble, there's this big oxidized batholith that's probably feeding a lot of the Pebble system. And so we see similar thing with similar scale at Tanacross. So zooming in to the property scale. So this is a geology map on the left side, and the black outline here is the alteration footprint. And this is really what got us excited about Tanacross, is that there's a huge amount of hydrothermal alteration. We've digitized a lot of the alteration footprints of other big porphyry systems. And so these are down here. You can see Pebble, that's the alteration footprint, and the deposit footprint, El Salvador, Butte, and Taka. So this is the Torres Bluff alteration footprint at the same scale. And so you can see that there's probably quite a bit of room to hide a significant porphyry system in that alteration. This is on the right-hand side. This is ridge and spur soil sampling that we did. And the dot colors are, we took clasts that were in the soil and just classified them if they're altered, unaltered, or unknown. And so the red areas are altered, the blue areas are unaltered. And I should say that in this part of the world, there was no glaciation. So this the rock has been sitting there for the last 70 million years and rotting away, so it's residual soils. And so the grid in the background is a sericite index that we did from the soil samples, and it kind of highlights areas of known alteration. It highlights this area quite well. And we have a porphyry deposit, the East Taurus system, which is sitting in here, which is a known porphyry. It's the same age as Casino, so there's a number of dates on it from 69 to 73 million years. And there's historic drill intersects of 239 meters of 0.3 copper, 0.23 gold, and 0.036 moly. In 2019, we stepped out from that and we hit 276 meters of 0.23 copper, 0.16 gold, and 0.036 moly. And so we have a number of targets up here that we will be testing this upcoming summer. When we look at the geophysics, so on the left side, this is the magnetics. And so there's this broad anomaly with similar strength to the east and west tourist areas. So that's in the circle here. Then we have ZTEM data, which is a electromagnetic survey. And you can look at different frequencies that tell you different things. So with that coincident mag high, it has a resistive area in the center with a conductive halo. And that conductivity is really mapping out quartz sericite pyrite alteration really well. And so we have a mag high resistor with alteration around the sides. That's a classic target to be a potassic core with magnetite with QSP alteration around the side. And then also as you go to lower frequencies, which tell you deeper, gives you deeper information. So the long wavelengths are looking about 1.5 kilometers to 2 kilometers deep. And there's a big deep conductor on here, which is similar to what you see in other porphyry deposits. So as a comparable here, this is the ZTEM data at Tanacross. This is ZTEM data at Pebble. And so you can see it has a really similar signature where you have a resistive core that's ringed by this conductivity. It's similar scale as well. So this is at the same scale. The maps are at the same scale. Then when you cut a section through this, you can see this is what Tanacross looks like through that, or it's the South Taurus target through that anomaly. And then this is what Pebble looks like. So it's got the exact same signature as Pebble, where you have a deep conductor, and then up top you have more of a resistor in the center with conductivity around it. So we're going to go up here this summer and drill test this, which I think is pretty exciting just because we have known porphyry mineralization all around this big geophysical target. So going to our Healy project, this is also in Alaska. It's about 19,000 hectares of state-owned land. We have a deal with Newmont where we're earning into the project. We can spend $4 million in the ground to get 70% of the project by December 2022. We're in the Tintina Gold Province. And so this hosts major gold deposits such as Donlin, which is about 40 million ounces of gold, Fort Knox. Pogo is just about 25 kilometers to the northwest of our project, and that's about a 10 million ounce deposit. So in terms of geology, like I was saying, so Pogo, about 10 million ounces here. It's a quite well-endowed district. The Goodpaster district sits within the Yukon-Tanana terrain, and it's a tectonic terrain of upper Paleozoic and older metasedimentary rocks, metavolcanic, and plutonic rocks that extends from central Alaska through the central Yukon and northern BC. And so Healy represents a newly discovered gold system by Newmont through systematic regional stream sampling across eastern Alaska in 2011. And so this red box here is the approximate outline of all the areas that Newmont sampled. So it was a huge stream sediment sampling program. And the Healy area was really one of the best anomalies that came out of that whole program. And so the project has multiple kilometer scale gold and arsenic antimony anomalies in soils, which is a typical metal association that you see in these types of rocks. So this is looking at stream sediment sampling, and there's three types of samples on this map. So the oldest is the blue samples, and this was 1967 to 1980. And these samples didn't pick out the Healy area. It did pick out the Pogo area relatively well. And then there were stream sediments done again in 1999 to 2007, and they also pick out the Pogo deposit and the Tibbs Creek area, which is another gold target that Tectonic Metals has. But they didn't sample the Healy area in that survey. And so during the Newmont program, these are catchments or drainage catchments of the streams. And so they're all kind of clustering in the same area. And we don't have the rest of this data, but they've told us this is one of the more significant anomalies that came out of that program. And so Newmont does a specific analysis. It's called BLEG, which is bulk leach extractable gold. And it really targets the silt clay, the superfine fraction of the stream sediments. And this reduces a lot of the nugget effect that you might have with a coarse gold particle getting into the sample. And so a lot of the historic data was -80 mesh, which is coarse, which tends to be a lot more nuggety and less repeatable. So zooming in, this is a geology map. So in the southeast, we have these intrusive rocks out here. The blue is in Ogden gneiss. And then we have these slivers of ultramafic panels that are coming up along these shallow thrust faults. And so in the center of the property, we have a number of different structural trends and intersections, which are probably important for gold. This is the soils that were done up until now. So there's been about 5,800 soil samples collected to date. The first program was a ridge and spur soil sampling program, which means you just follow the ridges and any of the spurs that come off of those ridges. And that gives you a good, decent first pass about what could be there. So from that ridge and spur soil sampling program, there were some areas to follow up. And so after subsequent soil sampling, this is kind of what they've turned into. And right now we have, it's down to, I think 50 meters by 50 meters on these grids. So zooming into here, in 2019, we carried out a reconnaissance RC drill program, and we only got a total of 800 meters in 10 shallow holes. So that was in the Bronx area right down here. And so the best intersect was 49 meters at 0.42 grams per ton gold. And so since then, we have carried out detailed infill soil sampling. We did a high-res airborne magnetic survey, and then we also did VLF and IP over specific targets. And so from this, I think this is all of the data that we need for drill targeting to go up and test these anomalies this summer. This is looking at the VLF data, which is an EM type survey, and it's been noted to be really successful up here at defining structures. And so in these areas, you can see the blue is the conductive areas, and so it's probably water that's percolating down fault zones or damage zones that's being picked up. But it's a really good way to map out the structures. And so on top of that, in the yellow outline, that's the gold and soil anomalies. So you can see where the structures are and where the gold is, and it's giving us some really good drill targets, I think. And so we're going to go out this summer and drill about 4,000 meters of diamond core and test all of these soil anomalies. The red lines here are our IP lines, and I'll show a little bit of that data on the next slide. So this is one of the IP lines at the spike and trig target. And so on the top here, this is the VLF with the gold in soils. And so the section here is chargeability in the IP. And so that's targeting disseminated sulfides. And so we see this big chargeability anomaly is lining up perfectly with this VLF structure. And then also this VLF anomaly here is lining up with this chargeability anomaly too. So we are going to drill across those, and I think that we will probably hit some gold. It's just how big and at what grade. And so this this figure on the bottom here, this is from the Pogo deposit. And so what you see at Pogo is that they have these shallow structures or shallow dipping structures, these ones, and then they have these steep structures as well. And it's really these shallow structures that have a lot of the gold. So the lease zone has produced a lot of the gold at Pogo. And so in this area, we're not sure if it's the shallow structures or the steep ones, but we're going to test a bunch of ideas here this summer. So the Healy project in highlights, so it's the right geology. So it's at this contact between metamorphic basement domes and Cretaceous intrusive rocks. This is where the Pogo deposit is hosted as well. We have low angle thrust faults and high angle northeast trending faults, which is similar to Pogo. This was discovered by systematic greenfields exploration. So it was really the Newmont data that got us in here and got them in here as well. And this is a completely greenfields area. There's no historic exploration filed, and there's no claims staked in the area. It's got a quite significant geochemical footprint, which is what I think we're always looking for. And so to compare it to something, this is the coffee deposit in the Yukon, and this was discovered by Kamenak, subsequently bought by Goldcorp, and now in Newmont. And so that's a 2.7 million ounce gold deposit. And then the Golden Saddle area in the Yukon as well. So that's 1.6 million ounces, and that's in white gold. So when you compare these to Healy, Healy is definitely similar in size and in concentration of gold in soil. So I think it's going to be a really exciting summer when we go up here and drill these targets. So just to kind of bring all of this together into, I guess, our strategy and things that we're kind of thinking about in these early stage programs. And I've kind of broken it down into 4 things. So where to explore, the strategy, how to explore, and recognition of success. So where to explore, I think there's really 2 big things, which are prospectivity and exploration maturity. And so prospectivity, this is looking geologic terrains that are fertile. There's a lot of ways you can do this. There's the detailed approach. So this would be using geologic and genetic models that have been built from the global record of mineral deposits. And you can do a whole bunch of fancy stuff like prospectivity maps and doing, any number of things to look at fertility. There's also a simplistic approach as well, is that if there's significant deposits in similar rocks, then the area is probably fertile. So the Abitibi Greenstone Belt is a fertile place because there's 280 million ounces of gold that have already been defined there. So we know that there's probably going to be more. Exploration maturity. So I think the biggest thing is understand what has been done previously. And if you don't know what's been done previously, it just adds a huge amount of risk, I think, to the current program that you're doing. Look in areas that previous explorers haven't looked. If you're just going back to the same place where people have looked before, your chances of success are going to decrease rapidly, I think. And then look in a different way than previous explorers have looked. So if everyone has flown EM surveys over an area and drilled EM targets, don't go fly an EM survey and drill EM targets unless there's been a significant deposit found in the area. And then I think a really important one is look under cover. And so when I say cover, that's some kind of cover sequence that's obscuring the bedrock geology. And that could be glacial till. It could be a later sedimentary, a lithified sedimentary package that's on top of the prospective rocks. So any kind of cover sequence. And so if there was a major deposit that was outcropping in these well-endowed or fertile districts, it would have been discovered decades ago. So it's better to look in places where people haven't looked, which is usually undercover. So in terms of strategy, I think exploring large areas on greenfields programs is probably the biggest thing, because greenfields exploration is like trying to find one needle in 10 haystacks. So the target that we're looking for is incredibly tiny when you look at the big scale. And so the solution to this is explore all of the 10 haystacks systematically, instead of picking one haystack. So to do that, ideally you're starting out with a large area. So that's hundreds to tens of thousands of square kilometers. And you are reducing that down systematically at each stage. And so there's a traditional adage, which came from research that Rio Tinto did quite a while ago, that 1 in 1,000 projects or mineral exploration projects becomes a mine. And I think that this is misleading. I think instead we should be thinking about endowment per square kilometer of prospective ground. And so if you're exploring a huge amount of prospective ground, statistically you will find something if your exploration tools are tailored to that area. And so that takes me to how to explore. So exploration tools, there's really 5 choices. It's geochemistry, geophysics, alteration, favorable lithologies, and structure. I'm going to go out on a limb and say geochemistry and alteration are best, because it's a direct confirmation that there's metals in the system or there's hydrothermal fluids in the system. Geophysics, you can have a lot of different physical properties in the earth that can give you geophysics anomalies. And so they can be red herrings a lot of the time. But if you have no mineralization in an area and you have geophysics that's extrapolating out from that no mineralization, it can be incredibly powerful. And so when you have no mineralization, for extrapolation, geophysics, structure, and lithology or lithologic associations are very useful at that stage. And so the area reduction has to be tailored to the exploration tools that you're using and that are effective for the deposit type that you're looking for. So if you're looking for a big porphyry deposit, it's a kilometer by a kilometer wide. That could be a good candidate for geophysics directly. You can get a lot of false positives as well, but at least it's a big enough target that you can look for it with airborne geophysics. If you're looking for a gold deposit, using airborne geophysics doesn't really help. Structure a lot of the time doesn't really help because the scale that a deposit is in compared to those data sets is just so small that it's really hard to find. So if you're looking for gold deposits, it's best to have some kind of geochemical vector towards an area. And then I think recognition of success is fundamental as well. So I think have to know what an exploration success is. And most of the deposits have been found after 2 to 3 rounds of drilling. And so the first round of drilling might not be spectacular. You might get 10 meters at 2 grams per ton or something like that. But that could be significant. And it takes, I think, a couple passes of drilling to orient yourself and kind of know where the best areas are. And so the first round of drilling, is it significant? That's really a fundamental question. Understanding the footprint, geometry, and scale of major deposits. So this is super important, and you do this by comparing to known deposits, case studies, exploration histories. And so we do a lot of this is looking at previous discoveries to see the steps that they took and the results that they had on the first pass to understand if what we have is significant or not. And then this all kind of leads to the decision point of when to continue and when to walk away. And so this is really one of the hardest decisions to make. A lot of the time you have some results that, are okay. They're not amazing, and you're not sure if whether to continue or not. And so this is really, it comes with experience, but I think you can make better decisions with the more data that you look at as well. And so the average greenfields discovery takes 3 passes of exploration, including surface work. So that's a bit of a rule of thumb. And so just to end it off, this is a little bit of, this is a slide on the Hemlo, or the David Bell part of the Hemlo deposit, which is a 20 million ounce gold deposit that was discovered in 1981. And so in the graph here, this is the GT intersects the grade thickness of all of the drill holes from the 1981 program, which was 132 total drill holes. And the Corona Resources and Murray Pesum, who was funding it, had the fortitude to keep this going, because at that time, the grades that they were hitting weren't spectacular. But on these initial drill holes, these are some of the assays that came out of it. So a meter, 1.7 meters at 39, a meter at 3 grams, 1.5 at 5 grams, 1.5 at 1 grams. And so that ended up being about an 80 GT hole, which, in those days, people weren't really interested in this kind of 1 to 5 gram. They were looking for 20 gram material. And so this is from the drill log of what was intersected. And so it was quartz sericite schist, fine grained quartz sericite schist with darker gray chloritic and fuchsite streaks. They talk about 3 to 5% disseminated sulfides, quartz veining, and VG. And so this goes from 130 to 176 feet. So this was a 15-meter zone of quartz sericite schist, but they kept hitting this on every hole. And so they were defining a system. They were very close to the heart of it, and the initial drilling wasn't especially spectacular, but this is basically drilling about a couple hundred meters away from a 20 million ounce deposit. So this is the thing, is recognizing when you're onto something. And I think the scale of alteration and mineralization that you see is important. So that's it. And I think there were some questions here, so I will answer these. Number one is, what are some potentially good indicators for young geologists that an exploration company would be good or not so good employer? Are there any clear red flags young geologists should be looking for when it comes to the company's projects, structure, etc.? Yeah, I think as the commodity cycle gets hotter and hotter and the commodities prices go up, there's more and more companies that just kind of pop up that aren't very serious companies. And I think a good way to look at it is the people that are involved, so the management. So look at what they've done before, their past successes, and look at their news releases to see what they've been doing. Look at their corporate presentations to see what they've been doing. And then I think, a big thing is researching the project. So if it's something that's been hit by 5 companies before and no one's ever found something significant, it's probably one of these things that people just kick around over the years to raise some money and go drill a few holes into, and then it just goes away again. It'll come back in 10 years again. So look at the people and look at the projects and look at the exploration history, I think, is the big thing. So number 2, do you think that in Canada we focus our exploration too much on historic mineral occurrences and the related areas and superficial outcrops that were potentially underexplored previously? Should we as geologists start being more innovative in our exploration techniques to find future deposits, or can we continue to rely on these historically identified exploration target areas? I completely agree with this. I think that in Canada we focus too much on historic showings. And this is something that the Australians do. They don't do this. They look at geophysics. They look at geophysics quite a bit, and they don't have much outcrop to look at. So they have to test geologic targets or go out and collect new information undercover. So yeah, I think the real potential going forward is undercover in some way and things that aren't outcropping. If it was outcropping, it would have been found before. That being said, there's always potential around known mineral deposits, stepping out, looking at a parallel structure, things like that. In terms of green fields, you really have to be looking undercover, I think. Number 3, how necessary do you think graduate studies are to a geoscientist's career? What doors can it open? So I'll be frank about this. Don't tell your professors I said this, but I don't think graduate studies necessarily help you. It can be helpful. It might not be helpful. So I think it really depends on the person's drive and what they want to do and how committed they are to it. And having a PhD really doesn't matter in terms of mineral exploration. I think it's experience that matters. So if you spend let's say 6 to 7 years doing a master's and then a PhD, that could be 6 to 7 years of experience that you had in industry that I think is probably more helpful. And when you're working in industry, you're also learning a lot. I haven't done a master's or a PhD, but it depends. If you want to be a consultant that's very specialized, then a PhD can be really good, or graduate studies. But typically, exploration is not specialized. You have to know all of the tools, and just being an expert in one doesn't mean that you're going to be a good explorationist, I don't think. So number 4, would you suggest working for a couple of years before returning to grad school? I would say that if you do go to grad school, that working a couple of years is very important because it gives you an idea of what industry is looking for. And if you've never really worked in the industry that much, it's kind of hard to understand how things work. And so you might start grad school and go down a path during a master's or a PhD that might not be applicable to industry. And then you come out and you did a master's and a PhD, but it doesn't really help you in terms of getting a job because it's so specialized in an area that's not really that applicable to industry. Number 5, out of the projects you've worked on, what deposit type did you enjoy the most and why? I worked in Ethiopia for a year and a half, and that was for VMSs, and I think that was probably the most enjoyable one, because with VMSs everything works. So in terms of alteration, they have big alteration footprints. They have geochemical signatures or very broad geochemical signatures. There's a lithologic association that can be used a lot of the time. So doing a lot of geologic mapping is really helpful. And then a lot of geophysics methods work for them as well. Number 6, how did working for a major company like Newmont differ from working for a more junior company? What are the pros and cons of each, and how did your experience level factor in? I would say that if you can work for a major company early on in your career, then that's a really good move to make, because you get an idea of what a major mining company looks for and how they think and how they operate, basically. So a lot of the juniors, I mean, now I'm a part of running one, and it's chaos. Everyone's just running around with like chickens with their heads cut off, just trying to deal with things, and it's hard to mentor anyone at this stage. But when you work for a bigger company, it's people have more time. They can mentor people or younger geologists a lot more. So I would say, as a learning experience, working for a major early on in your career is really good if you can land one of those jobs. Number 7, what compelled you to stay with your company for so long? What prompted you to move over to Kenorland? Given the breadth of deposit types you worked on, what skills have stayed constant throughout, and have some of those skills changed? I guess so. I was with Newmont because I was having a lot of fun. I was in the Arctic for 5 years, and we were doing a lot of geologic mapping, and that was really it was a huge learning experience of learning rocks in greenstone belts, mapping, a lot of things that you learn about in school, but putting into practice every day. And then I went to West Africa, so Burkina Faso and Cote d'Ivoire with Newmont as well, also looking for gold. And so I was doing a lot of mapping there as well, and targeting on greenfields programs, and that was fun. And then I went to Ethiopia after that with Newmont, and then after that I came back to Canada and worked in the Arctic in Nunavut again with some ex-Newmont people for a year, and then after that started Kenorland. So number 8, what's the most and least fun things about operating your own company? I'll start with the least fun. I guess it's all the administrative stuff that you have to deal with. It's constant, it's permitting, it's reporting obligations to the government. It could be contractors that have bailed or not performing. There's now that we're a public company, there's marketing things to worry about. There's shareholders to worry about, and it's a lot of things to worry about at once. So that's, I guess, the least fun parts. Oh, and accounting. I hate that. Not that I do a lot of it, but when I have had to do it, I hate it. And then the most fun, I think, is when you have a new idea, being able to act on it. And, I don't really have to go to a boss. It's our team, and we're all, we all decide on these things together. And so, when you have an idea, it's like, hey, this is pretty cool. Let's go stake this ground. And then, the next week we have our credit cards and we're acquiring hundreds of thousands of hectares of ground. I think that's pretty fun. So that's the questions. And I think that's all. So thanks for having me. And if you have any other questions, send them to Kevin, who can pass it on to me. Okay, thanks. Hope you enjoyed. Bye.